So at the end of lesson 1, we built a shallow neural network. And since then, we have learned a ton of theory on artificial neural networks. And so I think we can build quite a bit better neural network than we had then. We're going to start with it. So let's go into our Jupyter notebooks here and select the shallow net and Keras that we built at the end of lesson 1. Then we're going to duplicate it. Yes, I am sure I want to duplicate. And then we're going to go into that copy of our shallow net. So we're going to give it a better name. We're going to change it to, well, you can change it to whatever you want. I'm going to change it to intermediate net in Keras. Demo under the end there. And we can change the name at the top of the notebook here. So enter to get in there, and then change shallow to intermediate. You can add a note here. Now we're going to leave setting the seed the same. We're going to load the same dependencies. We're going to load the same data. But now we don't need to spend quite as much time looking at it because we understand the MNIST digits back and forward now. So let's delete some of these lines. You can use a quick Vim shortcut here, DD, to delete lines. So I'm going to do that. Delete all these lines where we're looking at X's and Y's and learning what they are. It's old hat now for you, isn't it? Same thing with the pre-processing data. We want to do the pre-processing, but we don't need to look at all the outputs here. So, and then we're going to design a new neural network architecture. So let's delete everything below the architecture. And then we'll go up to the top here. We're going to reset our kernel, reset all of our outputs so that we have a clean looking notebook to look at here. And then we'll go through them step by step. So you can use Shift-Enter to execute these cells. So let's set the seed. Let's load our dependencies. Takes a second. There we go. Then let's load the data. There we go. That took a second. It's done. And then we're going to pre-process our data. Bam, 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 done. And now we had our shallow neural network architecture here. How did it perform? Let's recap quickly. At the end of section 1.3, with this single hidden layer and just one epoch of training, we had 9.6% accuracy. Now, there are 10 digits in this data set, so that is slightly below chance. You'd expect 10% by chance, and we were at 9.6%. So that isn't great, but then we found that if we trained it for longer, for example, I trained it for 200 epochs, and at that point I got 86.6% accuracy, so that starts to sound pretty good. So in fact, our shallow architecture, with sufficient training, did a pretty good job. It was classifying digits correctly almost 9 out of 10 times, but I know we can do better. So let's make some of the changes that we talked about in the theory so far in this lesson. So one thing is we're using sigmoid activation here. So we used sigmoid when we were talking about theory in the beginning, but we also discussed that using one of these other neuron types, Tanch or ReLU, would be more efficient. So let's switch this over to Tanch. And our input shape stays the same, of course, because we still have images that are 28 by 28 pixels that we've flattened into a single 784 length array. Let's leave this as a shallow architecture with just one hidden neuron for now. And just to evaluate the performance of of changing sigmoid neuron to Tanch neuron here. So we've now compiled the model. Let's have a look at it. You can press A to insert a cell above. Have a model summary here. Okay, yeah, looks the same in terms of number of parameters as before, which is what you'd expect. And then we need to compile the model, and let's train it. Well, 200 epochs is way too long. But I can tell you that, so previously, after a single epoch, our validation accuracy was at about chance, as we discussed, 9.6%. But now we're seeing after that first epoch, 18% accuracy, which isn't good at all, but that's way better than we were getting with the sigmoid neuron. So it does indeed appear that with the tanh neuron, we are getting faster learning. Now, I can tell you, because I already know what happens when we get to the end of 200 epochs, you hit that same 86.6% accuracy after about 36 epochs. So after running over all the data 36 times, we exceed our performance after 200 epochs with the sigmoid neuron. And if you run this all the way for 200 epochs, it gets a little bit better. It gets to 88% accuracy and still slowly learning. But I think we can definitely do better. That's still pretty inefficient. So let's stop things here and make some more changes to our model. So another change that we talked about was using ReLU neurons. So we said that those are the kind of state-of-the-art neuron to be using. So let's give them a shot here. Let's change our activation here to ReLU, and we'll run this again and see what happens. So you want to restart your kernel and run all to make sure we're resetting everything. Now, after one epoch, not performing quite as well as a tanh neuron, 15% accuracy on the validation set, but it quickly kind of catches up. And because I've already run this, I can tell you that around the same time as the tanh neuron, it surpasses that 86% accuracy. So the ReLU neuron does it in the 38th epoch, the tanh neuron did it in the 36th epoch. It also gets to about 88% accuracy after 50 epochs, just like the tanh neuron. So for this kind of smaller network, we're not seeing much of a difference in performance between the tanh neuron and the ReLU neuron, but we're going to stick with ReLU anyway because we know from other studies that that tends to be more efficient, particularly with larger infrastructures. So let's leave that activation as it is. Now, what else can we try to do differently here? Well, one thing that I notice is that in our model compile step here, we're using mean squared error as our loss. Now, mean squared error is a synonym for quadratic cost. So the cost function that we're using in this network, the way that we're evaluating the degree of wrongness of the outputs of our neurons is this quadratic cost. But one of the things that we discussed in the theory at the beginning of this lesson was that cross entropy is far more efficient at learning. So let's try that one out instead here. So to make that change in the code, we change mean squared error loss here to categorical cross entropy. And then we can restart our kernel and run all. Let's see what happens. Here it goes. So now, wow, that's a huge difference. So before, whether we were using the ReLU neurons or the tanh neurons, we were seeing performance in the teens and then the 20s and the 30s in terms of validation accuracy in these first epochs. Now, bam, we change to the much more efficient learner in terms of loss from the mean squared error loss or the quadratic loss to cross entropy, and bang, we're getting much higher validation accuracy. So now we're seeing validation accuracy of 84% in the very first epoch. By the fourth epoch, we're seeing 90% accuracy, which is better than we were getting in the first 50 or 100 with tanh or ReLU neurons. So that's really promising. It is clear, in fact, it is clear that we have made a very positive change here to our network. The biggest single difference that we've made yet. Now, what else can we do here? So I can tell you if you run this long enough, after 50 epochs, you get to 95% accuracy that way. But it starts to slow down. So, 95% accuracy blows any of the results out of the water that we had before, but it's still quite a bit slower than before. So in those later epochs. and it doesn't seem like it's gonna be going up much higher than 95%. So what else could we try to do here? Well, we're still only working with one hidden layer. So as of right now, we're only trying one hidden layer in our network. We have our 784 inputs. We have one hidden layer with 64 neurons inputting into a softmax layer with a single neuron, or sorry, with 10 neurons, because we have 10 classes. And so let's add in another layer. So we do that here in this design neural net architecture section. So we can use model, add, and we're going to add another of the same kind of layer. So we're going to add another dense or fully connected layer. And this dense or fully connected layer is going to have 64 neurons. We're choosing a ReLU activation again here, of course. And those are all the parameters that we have to specify. We don't have to specify input shape again. We only need to do that in the first layer. So Keras does this incredible job of fitting TensorFlow in the background for us to enable all of this to happen seamlessly in this simple API for us here. So this is all we need to do, just adding that one line, and we've added in a whole new hidden layer. So let's restart and run all again. Because we've now greatly increased the number of weights in our model. Well, actually, not greatly. So before we had these 50,000 parameters already. Now we've added 4,000 more parameters. So it shouldn't take that much longer to train, actually. And we're seeing similar kind of performance after one epoch, 84%. But we start to see much higher than 95% results later on. So we hit 95% by 23 epochs here. And I can tell you, because I've run this before, that we peak at about 97.7% accuracy in the 133rd epoch, the 133rd run through the data. And then we begin to slowly see some decline in the training loss. So it seems like we kind of peak around 97, 98%. So there's one last change that I want to make here. And if you recall back to earlier in lesson 2, we talked about stochastic gradient. We talked about gradient descent as a way of learning how to minimize the cost function, how to minimize error in our network. One of the things we didn't talk about then, and we'll get into more detail on soon, is learning rate, which is essentially the size of the step that you try to make to minimize your error. Now, it might sound like a good idea to just always go faster. Why wouldn't you want to just minimize your error? But in fact, you can, if you choose a number that is too high, if you increase your learning rate too much, then you can start to miss the minimum. You'll step right over it. But let's do a little experiment here. And because I'm losing my patience for watching all these epochs, let's just see what happens if we make it a little faster. So we're going to ask it to make its steps an order of magnitude larger. We're going to reset the kernel and run all. And what do we get? So we can see that our validation accuracy in the first epoch is higher than ever before in that first epoch. And we're very quickly getting to that 97% that we were waiting dozens of epochs to get to with this slower learning rate. So I think that was a good decision. I think increasing the learning rate there was a good idea. We certainly aren't overstepping the minimum because we're still converging on this high validation accuracy value. And so that's pretty cool. I think that we've done pretty well based on the level of theory that we have under our belts to this point. So at the beginning of lesson 3, we're going to go through a bit more theory. I promise it won't get as crazy as at the beginning of lesson 2. And that touch more theory will equip us with the ability to have even higher performing deep neural networks. And in fact, we will become so adept that these MNIST digits will become too easy. We'll essentially have solved this MNIST problem, and so we're going to move on to the more complex Oxford Flowers dataset.